Good morning, everyone. Welcome to the webinar. Thank you for joining today's webinar titled Best Practices for Critical Dimension Measurements Using AFM. The webinar today is hosted by Oxford Instruments Asylum Research and presented by Dr. Marta Cochin and Dr. Ben Oler. Ben is a Senior Product Line Manager at Asylum Research, and Marta is a Senior Application Scientist at Asylum Research. Both Marta and Ben have decades of AFM experience. Before we begin the presentation, I'd like to cover a few webinar logistics. All attendees will be muted throughout the webinar, but we welcome your questions. Please submit your questions using the questions section of the GoToWebinar interface. You can submit them at any time, but we will only answer them at the end of the presentation. If you are directing your question to a specific speaker, please include that speaker's name with your question. We will address as many questions as possible at the end of the presentation. If you do have any connectivity issues, please be aware that we will record the webinar and you will be able to view it on demand at a later date. I also would like to take a few moments and mention that we have an AFM Advances Symposium this summer in Santa Barbara. It's from July 30th to August 1st. We also have begun accepting images for our 2024 image contest. Please submit your images online. For more details, please refer to our website. With that, thank you again for attending the webinar. I will now pass the controls to Ben.
Hi everyone, I'm Ben Oler. Welcome to the webinar. First, a quick outline of what to expect in today's presentation. I'll start with a brief overview of silicon photonics and what motivates the types of measurements that we'll be discussing. For those of you who aren't very familiar with AFM, I'll introduce AFM and the capabilities and advantages that it offers. Then I'll talk a bit about Asylum Research and the Jupiter XR, which is our AFM that's best suited to these types of measurements. And then before handing things off to Marta, I'll introduce some important factors that need to be considered when choosing an AFM probe. At that point, Marta will take over, and she'll present her work demonstrating various types of AFM measurements on silicon photonic devices and the analysis capabilities available for their interpretation. Finally, we'll wrap things up and have a question and answer session. Silicon photonics is a transformative technology that's currently seeing tremendous development activity. It refers to the transmission and manipulation of light, where silicon is used as the optical medium. While silicon has some intrinsic properties that make it well suited for optical applications, principally its high refractive index, the other driving factor is that these silicon photonic devices are largely constructed through conventional silicon on insulator processing techniques. Since the semiconductor industry has already built a very large and well-developed ecosystem for SOI processing, that's been an important enabling factor in rapid progress in the field. There are many different subcomponents in these photonic integrated circuits, but here in this talk we'll confine ourselves to the measurements on two types of nanostructures, diffraction gratings and waveguides. Currently, the technology is most widely applied to data and telecommunications because it can enable faster and more efficient data transmission. The data centers that power the internet and so many connected devices process tremendous amounts of data and consume massive amounts of energy in doing so. So there are very strong drivers for technology to improve that. But there are other areas where silicon photonics are ramping up or beginning to emerge. The technology enables optoelectronics that are used in display devices and smart glasses for augmented reality and virtual reality technologies. Silicon photonics can also be used in LiDAR sensors, which act as the eyes of autonomous vehicles. More broadly, the technology is finding its way into a variety of sensors, for instance, to monitor industrial processes or as biosensors. And longer term, the technology could be the basis for photonic quantum computing. So it's no wonder that research groups and companies worldwide are working with urgency to develop the technology and products that use it. As I've said, we'll largely be confining ourselves to discussing the metrology of waveguides and diffraction gratings. Though different in function, these often have similar nanostructures consisting of rows of parallel trenches. The terminology used varies with the specific types of waveguides and diffraction gratings. Sometimes we refer to the ridges or ribs of the device, or sometimes the trenches or slots that form the device. But whatever nomenclature is preferred, the critical dimensions and key parameters that affect performance often present similar metrology needs. Things like the height of the ridges, or alternately the depth of the trenches, the width of the ridges or trenches, and the edge variations of those, and related to that, the pitch of the structures. And then also the roughness of the various surfaces, whether that's the top of the ridges, the bottoms of the trenches, or the sidewalls. Scanning electron microscopy is the most commonly used metrology technique for these structures. It has the advantages of being fast and easy, and it has a high depth of field, so you can rapidly obtain images that show you, from a perspective view, what the structures look like. SEM can also provide compositional and chemical information about the materials in the structures. However, SEM is not very good at providing true three-dimensional metrology. You can only accurately measure dimensions in the plane view of the image. That means that to measure things like ridge heights, you must first cross-section the device and look at it from the end of the structure. Since you can't obtain 3D topography using SEM, you can't accurately measure roughness with it. Besides those limitations, there are some more general challenges around SEM sample preparation and sample charging during the measurements that can create additional difficulties. Atomic force microscopy is a technique that's often complementary to scanning electron microscopy. AFM has the advantage over SEM that it can directly measure 3D topography very accurately and at very high resolution, sometimes all the way down to the atomic scale. The principle of AFM is that it uses a sharp mechanical probe to trace the topography of a surface, line by line. This probe or tip is usually several microns in length and ends in a tip radius of about 10 nanometers. Because the AFM tip directly touches the surface, we can use it to measure more than just topography. We can use it to measure mechanical, electrical, magnetic, thermal, and functional properties of materials. This has made AFM a powerful tool in fields ranging from 2D materials to polymers to microelectronics. Some examples here showing that AFM can achieve atomic resolution on some samples. Here it's a calcite crystal face. Here is an ultra-high resolution current image of graphite atoms with a scan size of only 1 nanometer. In this example, carbon nanotubes are embedded in a polymer matrix. They aren't observed in topography, but you can see them and they appear when you measure the surface potential of the image. Similarly, by measuring dopant concentrations with scanning capacitance microscopy, we can visualize a defect in a transistor. Indeed, AFM can characterize many different types of samples by measuring mechanical properties, including Young's modulus, adhesion, viscoelasticity, and friction, thermal properties, including thermal conductivity, as well as observing thermal phase transitions, electrical properties, including conductivity, capacitance, magnetic and electrostatic force gradients, surface potential and work functions, as well as piezoelectric response. AFM can be run in these different operational modes with different probes and in different environmental conditions. Frankly, this wide breadth of capabilities is one of the things that can make AFM a little bit intimidating. Fortunately, when we consider silicon photonic devices, the use of AFM is typically pretty straightforward. Usually, AFM is used to make the metrology measurements that I previously introduced, critical dimensions of the ridges or trenches, and surface roughness. The principal advantage of AFM compared to scanning electron microscopy is that it can measure true three-dimensional metrology. The topography that we measure is fully calibrated in X, Y, and Z. Furthermore, the scale of the measurements is well matched to silicon photonic devices, ranging from picometers up to about 100 microns. AFM also typically requires little or no sample preparation, so there's no cross-sectioning or coating of the samples required. And though most of the measurements focus on metrology, we do have the capability to measure a wide range of material properties as well. In terms of disadvantages, historically AFM has been considered a slow and difficult technique. However, recent modern AFMs have made image acquisition much faster and much easier, such that it's now much more comparable to an SEM. When we consider silicon photonic devices specifically, there are a couple of challenges. One is that it can be difficult to measure sidewall roughness because it's not always straightforward for the AFM tip to reach these surfaces. There's also the possibility of tip-induced artifacts, which I'll discuss in just a bit. Before we dive into more detail around AFM metrology of silicon photonic devices, I want to take a few minutes to introduce Asylum Research to those of you who may not know us very well. We were founded in 1999, and since then our primary focus has been to deliver new AFM innovations that help drive both basic research and industrial R&D farther toward their goals. Not all of these innovations are directly applicable to silicon photonics, of course, but many of them are. Early on, Asylum led the AFM industry in developing closed-loop flexure scanners that greatly improved AFM scan accuracy and repeatability. Even today, many common AFMs use old piezo tube scanners and outdated sensor technologies that limit their performance. Another major thrust of our innovation has been around AFM scan speed. Conventional AFMs measure topography line by line at a maximum speed of about 1 or 2 lines per second, which means that a complete image takes 5 to 10 minutes or more to acquire. Asylum Research was the first company to introduce a fast scanning AFM in 2008 that could capture images over 10 times faster, meaning that images could now be acquired in less than a minute. Especially in industrial settings, that's a major productivity improvement that has helped make AFM a more practical technology for nanoscale metrology. In 2013, we developed a technology called blue drive photothermal excitation for improved tapping mode imaging. Tapping mode is the most commonly used AFM mode for measuring topography, and blue drive makes those measurements much simpler and more repeatable, which are important concerns for industrial AFM customers. Then, in 2019, we developed a critical technology for wafer scale industrial applications, which was our Jupiter XR AFM. Before Jupiter, there were small sample AFMs that offered high performance and large sample AFMs that could hold wafers but delivered significantly lower performance than small sample AFMs. That remains true for most large sample AFMs today, but Jupiter is the first and only large sample AFM with small sample AFM performance. What exactly do I mean by that? Well, as I said, the Jupiter XR is unique because it's a large sample AFM that can accommodate samples up to 200 millimeters in diameter while also delivering ultra-high performance and exceptional productivity. In terms of performance, Jupiter is an ultra-low noise AFM, which means that it can measure features with very high resolution. That's important for silicon photonics because modern deposition and etch processes are reaching lower and lower sub-angstrom roughness levels that are now beyond what could be measured with many conventional AFMs. At the same time, we can measure features over areas of up to 100 microns per scan, which means that we can characterize large areas of devices in a single scan. And then there's our exclusive blue drive technology, which makes these metrology measurements much simpler and more repeatable. I mentioned before that early AFMs were slow and difficult to use, and frankly, many still are, which continues to negatively affect people's perceptions about AFM. But with Jupiter, we can scan images over 10 times faster than most AFMs. Jupiter is also much easier to use, with an easy-to-follow workflow that guides you through setup and measurements. For wafer scale measurements, our 200 millimeter chuck is fully accessible, which enables the option of advanced automation capabilities to capture multiple images at many sites across a wafer. It's safe to say that if you've never used a Jupiter AFM, then you probably don't know how much AFM has improved over the last 5 to 10 years. And most of that improvement can be attributed to those Asylum Research technology innovations. Before I move on, I want to mention one recent addition to the Jupiter that's especially relevant to today's topic. It's a new AFM data analysis package called AR Maps, which is based on the Digital Surf Mountains Analysis package that you might already know from your other metrology tools. When it comes to critical dimensions analysis, this AR Maps package offers powerful and flexible recipes to consistently and repeatably analyze and report those parameters. In particular, there are advanced algorithms to measure trench critical dimensions and surface roughness, both of which I mentioned are key parameters for silicon photonic devices. On the next slide, I'll show you a very quick video of AR Maps, and then you'll also see used in many of MARTA's results. The key concept behind AR maps is that you can define and store analysis recipes for your different types of AFM measurements. Here we see an analysis where first the AFM raw data is plane fit and displayed. Then it moves on to critical dimensions analysis, where the desired measurements are chosen and precisely defined. And then those results are neatly exported in a tabular form for your sample report. Once set up, this same recipe can be applied to any number of future AFM measurements made on similar samples. As I said, you'll see more of AR maps in MARTA's presentation. The last thing I want to discuss before handing things over to MARTA is to introduce the concept of tip-induced artifacts in AFM measurements and how important it is to consider how AFM probe choice can affect your measurements. Probe choice is always important. There's truly no one-size-fits-all AFM probe. But with silicon photonic samples like waveguides and diffraction gratings, probe choice becomes even more critical. The simplest way to think about it is that the AFM can only accurately measure surfaces that the apex of the tip can reach. Many AFM samples are relatively flat with irregular rolling topography. Think about the grains on the surface of a silicon wafer or the grains in some thin film deposition process. Conventional probes can usually do a good job at measuring those samples because the tip is smaller than the features and fits well down between the features. But when samples have sharp sidewalls, deep trenches, narrow trenches, or high aspect ratio features, as many waveguides and diffraction gratings do, then conventional AFM probe tips can have a hard time tracing their surfaces. There are several ways that probe parameters can affect measurements. First, the tip length. Is the tip long enough to reach down into your features, down into trenches? Second, the tip half cone angle. You want it to be as small as possible to maximize bottom travel in a trench, as well as to avoid sidewall angle artifacts. Third, the tip radius can also affect bottom travel in trenches. And finally, tilt compensation. All AFMs mount the AFM probe at an angle, typically around 11 degrees. So you need to think about how the tip shape interacts with the sample and might affect sidewall angle measurements. If the tip is oriented so that the tip angles are symmetric, then at least any effect on sidewall angle measurements will be symmetric too. So let's first consider a conventional probe like an Olympus AC160 or our new Asylum Research Titan series probes. These probes have very sharp tips, which means that they can achieve very high resolution. But they do have relatively large tip half cone angles, which can make them a poor choice for deep and narrow features. Here, you see that the front and back angles of the tip are asymmetric, but when the probe is held for scanning at an 11-degree angle, that asymmetry is reduced. Nonetheless, since it's not fully tilt compensated, sidewall angle measurements will still be more or less affected depending on the scan direction. If you instead scan the tip perpendicular to the long axis of the probe cantilever, then the sidewall angles are fully symmetric. There may still be some effect on the measured sidewall angle, but it won't depend on the scan direction. Now, this is not to say that you can't use these probes to measure silicon photonic devices, only that you need to be aware of their limitations if your samples present you with these more challenging geometries. In those cases where samples do have high aspect ratio features or very steep sidewalls, then special purpose probes might improve your AFM measurements. As just one example, Nano tools offer special probes with high aspect ratio tips. Not only are the tips much longer and sharply tapered, but they're also typically fully tilt compensated, which means that the tip is vertical relative to the sample. So depending on your actual sample sidewall angles, you can eliminate or at least reduce artifacts in their measurement. The takeaway message here is that even on a world-class AFM like Jupiter, it won't make good measurements if you make a poor choice of probe type. You can image many types of samples just fine with conventional probes, but if your samples look more like the diagram on the bottom, then consider investing in special purpose probes that are better suited to those types of samples. Marta will be taking you through some actual examples that demonstrate these considerations, so for that, I'll hand off the webinar to her now. Thank you very much for your attention.
Thank you, Ben. In the following section, I will show you some examples of data acquired with different AFM probes, and then I will discuss the results with you. Let's look at the first data set. The sample is a waveguide. As you can see in the SEM images, it is composed of two parallel channels approximately 5 microns in width. Depth of these channels, or trenches, is around 600 nanometers. Both the width and depth of this waveguide are its critical dimensions, meaning that the properties of the waveguide depend on these dimensions and therefore need to be as close as possible to their design. This is where AFM becomes very useful, as it can accurately measure these dimensions. As we mentioned previously, AFM probe choice is an important part of AFM characterization. Here, the sample was imaged using a standard AFM probe, Olympus AC160. We decided to use a standard probe since the width of the trench is very large compared to its depth. So AC160 probe fits well. The AFM image is shown on the far right. The trenches are dark and the top surface is light yellow. Given this AFM image, critical dimensions were extracted from it using AR Maps software. AR Maps software offers two ways of measuring depth of features. The first one is to calculate the difference between the z-mean values of the top and bottom planes found in the image. As you can see here, the software found the two planes in the image, here colored in green and pink, and calculate the difference, which is 685.6 nanometers. The second method to determine feature depth is to do a cross-sectional height analysis of that image. Here the data is averaged over 5 lines. The resulting cross-section is shown in the middle of the slide, and several parameters are listed in the table below it. Mean depth is calculated to be 686.2 nanometers, which is in good agreement with the first measurement method I mentioned in the previous slide. Both ways of calculating feature depth yield depths that are greater than the values obtained from SEM images, and that by several tens of nanometers. This discrepancy could be attributed to the underestimation of results from SEM images. It is known that SEM images acquired with a tilt can affect distance measurements, so it depends on how the image was acquired. For example, what was the angle and position from where the user measured the area of interest? In other words, results are somewhat user-dependent. In contrast, during AFM measurements, it is the vertical position of the tip that comes into contact with the sample that is captured. The values depend mostly on the sensor noise, which is around 30 picometers for Jupiter XR AFM, and are not dependent on the user. Finally, I would like to bring your attention to the AR Maps table of results. It is automatically generated and provides a lot of information, including feature width, both top and bottom. Here we see 5 microns on the top, the sidewall angles, and feature pitch. There is also standard deviation as well as minimum and maximum values of different parameters, which provides a complete data set of the image. In this next example, we directly compare data obtained with an AFM probe that was poorly matched to the sample features with data obtained using an AFM probe that was well matched. The sample here is a diffraction grating with a repeating pattern of trenches. It is a silicon base with a layer of photoresist material on top of it. The expected dimensions are about 812 nanometers in depth and 300 nanometers width. We use the standard Olympus AC160 probe to image this grating. As Ben mentioned, AC160 probes have sharp tips, but their half-cone angle is rather large, which makes them inadequate for imaging of narrow deep features. The AFM data is presented here in 2D and 3D renderings, and as expected, the AFM data does not show the true dimensions of this sample. The 3D image clearly shows the pointy features which are not rectangular trenches observed by SEM. The images reflect the shape of the AFM tip and not that of the sample. So if you look at the SEM image here, the SEM image of the tip, you see the pyramid shape of the tip. The pyramid itself is 14 microns high, which is taller than the trench depth, but its shape prevents it from fitting into the trench and to measure the bottom of it. The cross-sectional analysis of the image indicates a depth of 226 nanometer instead of the 800 nanometers that is expected from the SEM measurements. The same sample was then imaged using a high aspect ratio probe from Nano tools called EBD4-200A. These probes are specifically made so that the tip is sharp and the half cone angle is small. The tip is also a pyramid, as you can see here in this SEM image, but there is a sharp 4 micron spike at the end of it so that the tip looks more like a needle, which allows for the characterization of narrow, deep trenches. The AFM data acquired with these probes looks much more like the expected deep trenches seen on the SEM image. The 3D AFM image and the associated cross-section analysis showed a flat trench bottom, indicating that the AFM tip did reach the very bottom of the trench. The analysis shows a depth of 805.5 nanometers, which is close to the 812 nanometers measured from the SEM image, and is much larger than the 226 nanometers that was measured with the poorly matched AC160 probe. Even though the bottom of the trenches was reached, the width is significantly smaller at the bottom compared to the top. This could be real tapering of the trenches, but unlikely, and could be verified by SEM. It is more likely that the long needle-like tip has a larger half-cone angle than predicted. It is also possible that the needle got contaminated during imaging. Either way, this direct comparison of data using two different AFM probes on the same area of the sample demonstrates the importance of choosing AFM probe to match the critical dimensions of features that are being measured. We also examined the sample where the photoresist was removed. Since the resulting features are relatively wide compared to their depth, we used a standard high-resolution probe Olympus AC55. The bottom of the trenches here was reached, which indicates that the AFM tip dimensions were correctly matched to this sample. Trench depth was measured to be 229 nanometers, which is about 15 nanometers deeper than the depth estimated from the SEM images. We assume that the AFM data is accurate, as the AFM tip physically contacts the sample at the top and bottom of the features. The analysis of the data was simple and fast using AR maps, as the table with results and statistical analysis is automatically generated once the cross-section position is chosen on the AFM image. Besides critical dimensions, AFM can provide additional information about the sample morphology. In this example here, we notice irregular bumps on the ridges of the sample, shown here with the orange arrows. We asked ourselves if it could be sample contamination. So a comparison of cross-sections from the ridge and from the bottom of the sample shows that the material is not on the same size scale, indicating that it probably didn't come from the same source. We hypothesized that the sample might have some environmental contamination overall, but the material on the ridges is leftover photoresist due to incomplete removal. In this last example, we performed surface roughness analysis. In silicon photonics, higher roughness results in increased light scattering, which in turn can decrease device efficiency. So it is important to monitor any changes in surface roughness. This sample has a silicon base and photoresist forms its ridges. The height difference between the two levels is expected to be around 730 nanometers. AR maps cross-sectional analysis of the AFM image shows a height difference of 756 nanometers. When assessing sample roughness, tip sharpness is the key tip property to consider. It is often defined as tip radius, meaning the smaller the radius, the sharper the probe. Since we are not constrained here by narrow trenches, we used an Olympus AC55 probe, which has a small tip radius of about 5 nanometers, but a large half-cone angle. Once the AFM image was acquired, AR Maps software was used to determine the ISO standard surface roughness of both regions. As expected, the silicon is smoother with a roughness of about 0.28 nanometers versus 0.86 nanometers for the photoresist. This finding is not surprising as the photoresist texture is also seen in the SEM image, but it is only the AFM data that provides quantitative surface roughness values. In addition to surface roughness, we observe that the silicon portion of the sample is not as pristine as anticipated. After adjusting the color scale, contamination became more visible on the silicon surface. So you can see that the AC55 probe allowed for the characterization of sample dimensions and at the same time was sharp enough to reveal the subtle contamination on the silicon portion of the sample. This example shows the advantage of AFM characterization over SEM, as only AFM can provide direct measurements of both critical dimensions and quantitative surface roughness. One last thing about surface roughness measurements. Here we focused on the bottom of the trenches and the top of the ridges. However, there is also a lot of interest about sidewall roughness. As you can imagine, obtaining trench sidewall roughness is more complicated due to sample geometry. If you would like to learn more about sidewall roughness measurements, please tune in to our next webinar, which will be on June 12th. With that, I'd like to summarize and conclude this webinar. We looked at real data examples, which hopefully convince you that AFM can accurately measure critical dimensions and surface roughness of waveguides and diffraction gratings. We discussed the importance of AFM probe choice and how tip parameters should be matched with sample feature dimensions. And finally, we introduced AR Maps software and used it for all of the data analysis that was shown in this webinar. So thank you for your attention, and before we move to your questions, I have a couple of quick announcements in the next slides. We recently released a new line of AFM probes, the Titan series. It is a direct replacement for Olympus probes that have been discontinued. Please check out our online probe store for details and pricing. If this webinar was interesting to you, you can now have a look at our newest application note about critical dimensions and AFM probe choice. And finally, as I mentioned before, if you want to learn more about surface roughness and sidewall roughness specifically, don't miss our June 12th webinar where we'll talk about slanted diffraction gratings and sidewall roughness measurements.
I'd like to thank both of our speakers for their presentations. Now we have time to answer some of the questions that have been submitted. If you have yet to submit a question, please do so now in the questions tab of the GoToWebinar. So, first question, is it difficult to use high aspect ratio AFM probes?
I can answer that. So, high aspect ratio probes are handling wise, they're very similar. to a normal probe in terms of picking them up with tweezers. There, of course, needs to be a little bit of care taken when choosing the settings, but in general, it's not that much different from using regular probes.
Okay, so we have a few questions about imaging mode. What imaging mode was used to acquire the images in the presentation?
So all the data that you've seen in the presentation here, all the images were acquired in tapping mode. So it's a intermittent contact mode. Yeah, all of the images here.
And so do you prefer tapping mode over contact mode when it comes to trench measurements? And could you also specify which technique you prefer for roughness measurements?
So the idea with imaging features that are very deep or very high, however you see it, is to be able to track the features, but also to be able to preserve your tip, because you're using these specialized tips that are needle-like. In this case, using tapping mode imaging, because it's a gentle technique, and it's with a lot of control over the amplitude, you'll be able to image the features easier than if you, for example, try to image the features with contact mode, where the tip is in continuous contact with the sample. So there's more chance of actually breaking the tip, or damaging it, or picking up some dirt, for example. And so being able to image in tapping mode is preferable for specifically for these high features or deep features. In terms of surface roughness images, we also tend to image in tapping mode, just because we want to preserve the tip sharpness, which is important for these types of measurements.
Great, and kind of along the same lines, did you use Blue Drive for tapping mode?
In some of the images I did, some I did not. It just depended on the image. But in you should be able to use either Blue Drive or Piezo Drive. The advantage of using Blue Drive is that you have better control of the amplitude, which means that you're actually having you're more gentle on your surface, on your tip, just because you have a good control or better control over the amplitude and the set point that you have for your images.
Great. And would you, for the tapping mode images, what amplitude did you use for the images, and how important is selecting the right amplitude?
So the amplitudes are actually high, just because you can um, you can think of it as you want your cantilever to oscillate as much as it can, so that it can go into the feature and then come out. So usually what we do is we set the amplitudes to be high, and the set points to be a percentage of that amplitude, so you can still achieve tapping, which is not uh, too harsh on your sample, just by having an amplitude that is high and the set point that is decreased just by a fraction of what it was in free air. In terms of values in nanometers, I don't have the values now, but you try to get them in the I would say hundreds. You can nanometers probably. You can as much as you can get from your cantilever. Usually you can try that.
Okay, great. So there's a few questions about the cantilevers themselves. How Do you have to image at 90 degrees? So in one of the presentations, I think it was your section, Ben, you talked about the asymmetry of the tip. How important is it to image at 90 degrees?
Well, so it really does come down to the tip that you're using. So, different tips have different geometries. So in some cases, like that one example I showed, the tip will be symmetric if you scan at 90 degrees. In other cases, if the tip is fully tilt compensated, then it'll also be symmetric from front to back. So it really does depend on the probe. And of course, then ultimately it matters too, what you're trying to measure. So if you're trying to measure the sidewall angle, and the sidewall angle is gradual enough that you can accurately measure it with the probe, then it'll be better to measure it with whatever sides of the tip are symmetric. So in some cases that will be just side to side with the 90-degree angle scanning. But again, for the tilt compensated probes, you'll be able to scan 0 degrees from front to back. So yeah, that's kind of the point of that discussion is you have to think about the individual probe that you're using and how that compares to your sample features.
Okay. And another question, could you please elaborate on the force constant choice? I'm assuming it's the spring constant.
Right. So in terms of tapping mode imaging, this is a little bit less important than it would be in the case if the imaging mode would be a fast force mapping or just performing force curves on a sample. There you would have to really think of how stiff your sample is versus your cantilever, and then you would want your spring constant to be high so that you're measuring the deformation of the surface and not your cantilever. But in the case of tapping mode imaging, as is the case in these results shown here, uh, we focus more on the tip shape, tip height, than on the spring constant. It happens that the spring constant here are in the 20 newtons per meter. But again, it's more to focus on the other properties of the probe than the spring constant in this case.
Okay. Marty, you also mentioned that there's a chance of tips getting dirty. Is it possible to clean the tips?
Yes, so it's not necessarily easy, but there are ways to try and regain some cleanliness of your tips. Uh, you can try placing your probes in a plasma cleaner, for example, or under UV light for some period of time, and hope that whatever contamination, if it's organic, it will be burned off or oxidized. One thing to keep in mind is that when doing so, you might change the chemistry of your of your tip, or it can even damage or dull your tip just because it's yeah, things can happen. But in theory, it is possible. So you can definitely try instead of throwing your tip away right away.
Okay. Are there any special considerations for preparing samples for critical dimension measurements?
I guess sample size, depending on the AFM that you have available. Sample size is one consideration. So you want it to fit in your AFM. You preferably, as for any AFM measurement, you want your samples to be clean. So if there were any processes that were happening, any I don't know, polishing or anything that was happening, you want to make sure that there is no material that is covering your sample, because then you have a chance of dirtying your tip and losing the resolution or even losing your tip. Can't really think of anything else specifically for these kind of measurements, but as for any AFM measurement, clean surfaces and the right size to fit your AFM.
Okay, great. So you suggested Jupiter for these measurements, but is there any reason I couldn't use my cipher?
So I could take that one. So yeah, we've focused on Jupiter here because, as Marta just mentioned, many of these samples are fabricated at the wafer level. So sometimes uh, it's a big advantage to be able to look at them while they're still in that form, or maybe still cut into relatively large um, coupons. Um, that said, certainly with Cypher, if you're willing to cut down your sample to fit on a small sample AFM like a Cypher, it'll work as well. I guess the other consideration would be the maximum scan size. So for Cypher, that's 30 microns in XY range versus 100 microns XY range on a Jupiter, which obviously imposes a limit on how large of samples you can look at in a single image. Other than that, yeah, really all the considerations are the same. Cypher supports all of the same imaging modes. It also features Blue Drive as well. So yeah, you can absolutely image these types of samples on a Cypher as well.
Okay, great. So there's a couple of questions about scan speed. So do you need to scan slower when imaging trench features?
You probably want to slow down in comparison to imaging a perfectly flat surface, just because you want to make sure that you're preserving your tip, so you give it a little bit more time to react to the very high feature, very deep trenches, for example. Uh, it doesn't mean that you have to go extremely slow, but a little bit slower. So, for example, if you would image a perfectly flat wafer, you would probably scan easily at 5-10 hertz. If you're imaging trenches, you probably want to slow down to 1-2 hertz, just so that yeah, you have a little bit more time to react and preserve your tip.
Okay, great. There's several questions about AR maps. First one is, can I analyze several images automatically in AR maps?
I could take that one. So yeah, that's one of kind of the beauties of AR maps, is that once you define one of these analysis recipes, you can apply it to as many other images as you like. So it can generate tables like those ones that Marta was showing you, where it shows the critical dimensions for a series of different images. So, assuming that the samples have, similar features and you're doing the same analysis on each image, then yeah, absolutely. That's one of the real benefits of using it, is that instead of analyzing all of your images one by one, you can really automate a lot of that. And not only does that save you time, but I'd also emphasize that that helps make the results more consistent as well, so that you don't have sort of operator to operator differences, and even just differences in how an individual operator might set up the analysis each time they sit down. This way, they're always using exactly the same settings, exactly the same steps.
Okay. And also, can AR maps be used with the MFP 3D origin data?
Yeah, so as I mentioned, AR Maps is a new software package for Asylum. Right now, we are including it standard with Jupyter systems moving forward from now. That said, it's compatible with images from both our Igor AFM software and our Ergo AFM software. So it'll analyze any of our AFM images from either of those software packages. So that includes the MFP3D, our Cypher, Jupyter, and then also our new Vero AFM.
Okay, great. Because that was actually one of the other questions, whether you could use Igor's files or Ergo. So the answer is yes, both can be used.
Absolutely.
So, okay, great. So are there other AFM modes that would be useful to characterize critical dimension features electrical nanomechanics or any other technique that AFM can provide?
I mean, depending on what is the interest of the sample. For I can think of if you're in the examples we've seen, we had these areas which are silicon and other areas that are photoresist. So you could probably, if you're interested in seeing are the materials different on different areas of your samples, your trenches, you could probably use mechanical imaging modes to see if there's any difference in the mechanics of the sample, which would give you information of which type of material is being used. Yeah, again, depending on how the samples are prepared, you might want to also look at um, the conductivity. One thing that you have to keep in mind is that you have to have the right probe if you want to do, for example, electrical measurements, and it just makes it maybe a little bit more complicated to choose your probe so that it's really sharp, really small half cone angle, and it's also conductive if that's what you're interested in measuring.
Okay, another question. Can you talk a little bit more about why AFM is more accurate for measuring the trench depth than SEM? I think we saw some different numbers in the presentation, and which data set should we believe?
This actually, we had a couple of discussions with our colleagues at our sister company, who Plasma Technology, who provided the samples that we were imaging, and the differences that we're seeing are probably due to the fact that the distances may be underestimated in SEM measurements, just because, as Ben was explaining, the SEM images, depending how are they taken, from which angle, from which side, you can have a little bit of distortion, and then the measurements that are made from the images that were acquired. So it's a little bit of a two-step process. Whereas with AFM, it's the AFM tip, AFM probe that touches the surface physically. So it touches the top surface, the bottom surface, and we obtain the difference in those different surfaces, and this is done by a sensor. So there's much less user interpretation or user I guess input when acquiring the data. So I think the data that you're seeing SEM is good data. However, it might be underestimated in some instances.
Okay, next question. What is a typical surface roughness for silicon photonic surfaces, and what is the limit for AFM to measure roughness?
So I'm maybe not the expert on all things photonics, but from what you've seen in the presentation, these are the roughnesses that I saw on these specific samples, which were if I remember, were below nanometer. In terms of what are the limits of AFM and roughness measurements, it really depends on the um, base noise of the AFM. So uh, in the case of Jupiter, the level, the base noise that we see is around maybe 30 picometers. So you can go anywhere that is a little bit higher than the noise floor. You're able to measure it if you have the right conditions and a quiet environment. So really, the having a sharp tip, having a quiet and a low noise floor instrument allows you to measure very, very, very small roughnesses.
Okay, so there's another question. How do you obtain sidewall roughness?
If you can just thinking of sidewall roughness, you can see that there is a geometry constraint that is not easily it's not easy to do that with AFM, where we're usually imaging from the top. We'll talk about more about how we can overcome this difficulty in our next webinar. So I won't talk about it right now, but yeah, tune in and we'll talk more about that.
Okay, great. So I think that answers all of the questions that have been submitted. We're also coming down to the hour. So I'd like to thank our speakers, Marta and Ben again. I'd also like to thank all of you for joining us today with this webinar. I just wanted to mention one more time before we close that we have our upcoming AFM Advances Symposium that will be this summer, July 30th through August 1st. Registration is open and we are still accepting late poster abstracts. We're also now accepting images for our 2024 image contest. Prizes are still available for the first 25 submissions, so I encourage all of you to send in your beautiful AFM images. The winners will be announced during the conference this summer. So please check out our website to learn more about our conference and image contest. The links have been added to the chat, so please click on those. Again, I'd like to thank all of you and have a wonderful day. Thank you.
Thank you.
Thank you.